The interconnection board inside the accumulator of our racing car is a very critical part, as it is in direct contact with the battery cells. The cells weld onto the big copper pads of the ICB, which needs to handle the large currents of the accumulator. The cell tabs are fed in pairs through the slits inside the ICB and then welded in place. For this, we use laser welding, as it guarantees a strong bond that can handle a lot of current, but it's also very safe as we are working with battery cells that can get out of control at any moment. For this laser welding, the ICB needs some very special manufacturing, where the copper pads are thicker than the rest of the PCB. Thanks to our partner AQC and their expertise, we can seamlessly work with such a design and get them manufactured in record timing, along with all our other PCB needs. With 24 cells attached to the ICB, this gives us a full cell stack. We have 12 of those inside our accumulator, creating the 600 volts that our car runs on. Each cell stack also gets one satellite on top that measures all the voltages and temperatures of the cells.
This year we had to make multiple changes to the ICB design, both to improve the cooling and because of multiple rule changes from the competition. By increasing the spacing between the bottom of the ICB and the cells, we increase the airflow past the cell tabs, thus increasing the amount of heat we can extract from the core of the cells. Along with other improvements of the URE20 accumulator, like full ducting, we managed to improve the airflow past these critical parts with 147%. With the changes of this year, we have had to move the temperature probes from the top of the cell tab to the bottom as close to the cell body as possible in order to get an accurate measurement. This complicates the manufacturing process because we have to bend the cell tabs in a certain way. To streamline this process and ease manufacturing, we use 3D printed tooling to circumvent issues.
Manufacturing the ICB is actually quite a unique challenge for us. It's not often that you get the request to weld on a PCB. But to realize this, we looked at the data, we consulted our production experts, and we found that a structural and electrical connection should be possible that guarantees that it's possible to weld on a PCB. In order to achieve a structural connection for welding, we would need about 500 micrometers of copper, which for reference is about 15 times the normal layer thickness. And for this we considered various production approaches across different iterations. This is where AQC comes in quite handy as a one-stop shop for electrical engineers when it comes to PCB manufacturing. We don't just manufacture and do DFM checks, we actually do version control. So across iterations we knew that from the first try, which was a rejected type, what we could improve on in order to make the design manufacturable, and what we could improve on further to make it a good design. For this we switched from an additive manufacturing approach, where we grow layers of copper on top of one another, which is normally done for PCBs. We switched to a subtractive manufacturing approach, where we etch away copper, and as we could immediately see, the result was a lot cleaner. Once a design comes into the AQC office, we have a lab at our disposal with a great number of equipment to test the PCB in all kinds of ways. We can do the simple things like visual inspection or thermal shock tests, but also the more complicated things required to really inspect the quality of a PCB as special and complex as this one. For instance, we do microsections where we cut a PCB in half and put it under a microscope to check the layer each individually, or we can make an entire X-ray composition shot of the PCB. With the ICBs due to arrive any day now, we are already curiously awaiting what crazy project URE will come up with next.